Download this code from codegive.com, link in the description below. OK, let's delve into the Back to Basics, Overload Resolution presentation from cppcon 2021, delivered by Deane and Jason Turner. This is a fundamental concept in C++, and a solid understanding of it is crucial for writing clear, efficient, and predictable code. I'll break down the concepts, provide detailed explanations, and include illustrative code examples. What is overload resolution? Overload resolution, also known as function overload resolution or sometimes overload selection, is the process by which the compiler chooses which function to call when you have multiple functions with the same name, but potentially different parameter lists. This is a cornerstone of polymorphism in C++. Why is overload resolution important? Asterisk flexibility and code reuse. Asterisk it allows you to provide different implementations for the same operation depending on the types of arguments you pass. This promotes code reuse and reduces the need for creating many functions with slightly different names. Asterisk clarity and readability. Asterisk well-defined overload sets can make your code more expressive and easier to understand. Asterisk abstraction. Asterisk it helps in creating abstractions that hide the underlying complexities of different implementations behind a single interface. Asterisk extensibility. Asterisk you can add new overloads to existing function names without breaking existing code that uses the original overloads. The overload resolution process, a high-level overview. The compiler follows a specific set of rules to determine the best match when you call an overloaded function. Here's a general outline. 1. Name lookup. Asterisk the compiler first finds all the functions with the specified name that are visible in the current scope, taking into account namespaces, classes, etc. 2. Argument dependent lookup, ADL. If the function call involves types defined in a namespace, the compiler also looks for functions in that namespace, even if they aren't explicitly brought into the current scope. ADL is crucial for making operators work with custom types. 3. Viable functions. Asterisk the compiler identifies the viable functions. These are the functions that asterisk have the correct number of parameters. Asterisk for each argument, a conversion exists to the corresponding parameter type. Conversion may be an exact match, promotion, standard conversion, user-defined conversion, or ellipsis conversion. 4. Best viable function selection. Asterisk the compiler then tries to determine the best viable function based on the rank of the conversions required for each argument. This is where the complex rules come in. The goal is to find the function where the arguments can be converted to the parameter types with the least amount of conversion effort. 5. Ambiguity. Asterisk if no single best function can be found, i.e., 2 or more functions are equally good matches, the compiler issues an ambiguity error. 6. Deleted functions. Asterisk if the best viable function is marked as delete, the compiler will produce an error, often saying that you are trying to call a deleted function. The ranking of conversions, the key to overload resolution. The heart of overload resolution lies in how the compiler ranks the conversions needed to match the arguments to the parameters. Here's the typical ranking, from best to worst. 1. Exact match. Asterisk no conversion required. Trivial conversions. Array to pointer decay. Function to pointer decay. Adding / removing const, volatile, or restrict qualifiers. These are called qualification conversions. 2. Promotion. Bool to int. Char, short, and unscoped enumerations to int. Flow to double. 3. Standard conversions. In order of preference. Numeric conversions, example int to double, double to int. Generally, conversions that preserve value and precision are preferred over those that lose information. Asterisk pointer conversions. Asterisk derived class pointer to base class pointer. Asterisk pointer to void asterisk. Asterisk conversion to bool. 4 user-defined conversions asterisk. Asterisk conversion functions defined in a class, example operator int, const. Asterisk converting constructors, constructors that can be called with a single argument. 5 ellipsis conversion asterisk. Asterisk using, varargs, to match arguments. This is generally the least preferred. Detailed examples and code demonstrations. Let's illustrate these concepts with C++ code examples. Explanation of the examples. Asterisk foo overloads asterisk the compiler chooses the foo function that matches the type of the argument most closely. If you pass an int, foo, int, is called. If you pass a double, foo, double, is called, and so on. Asterisk bar example, promotion when you call bar, 10, the compiler prefers the bar, long, function because an int can be promoted to a long, a relatively safe and inexpensive conversion. Asterisk baz example, standard conversion when you call baz, 5, the compiler uses a standard conversion from int to double. Asterisk cux example, qualification conversion the cux function takes a const int and passing an int x is an exact match due to qualification conversion. Asterisk myint example, user-defined conversion the myint class has a conversion operator int, const. When you call quoques, myint, the compiler uses this conversion to convert the myint object to an int so that it can call quoques, int. Asterisk ADL example asterisk the ADL underscore func is not declared in the main function's scope. However, because the argument myobj is of type mynamespace mytype, the compiler searches for functions named ADL underscore func in the mynamespace namespace. This is argument dependent lookup, and it allows the compiler to find the ADL underscore func defined within that namespace. Asterisk ambiguous example asterisk if you uncomment the line ambiguous, 1, 2.0, the compiler will report an error because it cannot decide which ambiguous function to call. Both functions require one promotion and one standard conversion, making them equally good, or bad, matches. Important considerations. Asterisk implicit conversions can be tricky asterisk overload resolution can become quite complex when multiple implicit conversions are involved. It's essential to understand the ranking of these conversions to predict which function will be called. Asterisk explicit casting asterisk if you're unsure which function will be called, you can use explicit casting to force a particular conversion. This can improve code clarity and prevent unintended behavior. Asterisk enable underscore if ensfany asterisk template metaprogramming techniques like std enable underscore if ensfany, substitution failure is not an error, can be used to conditionally enable or disable function overloads based on the types of the arguments. This provides fine-grained control over overload resolution. Asterisk the explicit keyword asterisk using the explicit keyword on constructors prevents them from being used for implicit conversions. This can reduce unexpected behavior in overload resolution. Asterisk deleted functions asterisk using delete is a way to prevent certain function overloads from being selected. This can be useful for preventing unwanted conversions or disabling copy/move operations. Asterisk order matters asterisk the order in which you declare overloaded functions does not affect overload resolution. The compiler will consider all visible functions with the same name when making its decision. The order of declarations only matters if ADL is involved, and it is then to determine the scope the name belongs to. Code example using enable underscore if. In this example, The enable_if mechanism selects the appropriate process overload based on whether the template argument t is an integral type or a floating point type. If you try to call process with a type that's neither integral nor floating point, like const char asterisk, you'll get a compilation error because no suitable overload exists. Key takeaways from Ben Deane and Jason Turner's presentation. The cppcon presentation emphasized the following points. Understanding the fundamentals. A solid grasp of the overload resolution rules is essential for writing correct and predictable C++ code. Minimize ambiguity. Design your overloaded function sets carefully to avoid ambiguity. Use explicit wisely. Use the explicit keyword to control implicit conversions and prevent unintended behavior. Consider SFNI for fine-grained control. When you need advanced control over overload resolution based on type properties, SFNI is a powerful tool. Tools can help. Modern C++ development tools, compilers, IDEs, static analyzers, can often help you identify potential overload resolution issues. In summary, overload resolution is a crucial aspect of C++. By understanding the process, the ranking of conversions, and the tools available, you can write cleaner, more maintainable, and less error-prone C++ code. Practice with examples, and don't hesitate to consult the C++ standard when you encounter complex scenarios. Remember to prefer clarity and explicitness when dealing with overloaded functions, and avoid situations where overload resolution becomes overly complex or difficult to reason about. Remember to use the explicit keyword with constructors.